What if one of history's most famous plagues wasn't plague at all? For over 2,000 years, historians have debated what killed tens of thousands of Athenians in 430 BC. Was it smallpox, bubonic plague, some kind of hemorrhagic fever like Ebola? Every theory seemed plausible until scientists extracted DNA from the teeth of plague victims buried in mass graves. What they found wasn't what the history books told us, and it rewrites our understanding of one of the ancient world's most devastating outbreaks. In 430 BC, Athens was at war. The Peloponnesian War had just entered its second year, and the city was swollen with refugees fleeing Spartan forces. Overcrowded homes, poor sanitation, and relentless summer heat created perfect conditions for disease. Then the sickness arrived. Ancient accounts describe something horrific. Fever struck suddenly. Victims developed severe headaches, inflamed eyes, and bloody throats. The disease attacked the stomach, causing violent vomiting and diarrhea. Many broke out in pustules and ulcers covering their bodies. Some went blind. Others lost fingers, toes, or even their memory. The dying collapsed in the streets. Bodies piled up faster than survivors could bury them. The Greek historian Thucydides witnessed the plague firsthand and recorded its progression in devastating detail. He described how physicians who tried to help the sick often died themselves, how entire households were wiped out, how desperate survivors abandoned the bodies of loved ones in temples and public spaces because there was nowhere else to put them. The outbreak killed approximately 1/4 of Athens' population, possibly 75,000 to 100,000 people. It struck 3 separate times over 3 years. Among the dead was Pericles, Athens' greatest leader, whose death in 429 BC marked the beginning of the city's decline. For centuries, identifying the pathogen seemed impossible. Historians and physicians could only work from Thucydides' written account, matching his descriptions against known diseases. But without physical evidence, every theory remained speculation. For generations, many believed the Plague of Athens was smallpox. The logic seemed straightforward. The rash, fever, and rapid spread fit descriptions known from later outbreaks. Historians argued that smallpox had appeared in the ancient world earlier than previously thought, hidden in the chaos of war. The theory held for decades, but it collapsed once genetic material from Athenian graves was finally tested. No trace of the smallpox virus appeared in the ancient DNA, and several symptoms described by Thucydides, particularly the severe intestinal bleeding and the pattern of mortality, didn't match smallpox at all. Other theories followed. Some proposed typhus because it thrives in filthy close quarters, exactly like wartime Athens. Others suggested measles for its rapid spread through crowded populations. A few argued for bubonic plague, the bacterium behind later medieval outbreaks. Each theory had arguments in its favor, yet none fully matched the symptoms or timing described in ancient sources. Then came a more dramatic proposal. Some researchers suggested an Ebola-like hemorrhagic fever. Ancient reports of bleeding, pustules, and extraordinarily high death rates seemed to fit. The comparison was powerful because Ebola terrifies us today, and imagining it in ancient Athens gave the plague new horror. Yet, the DNA analysis found no trace of filoviruses, the family that includes Ebola, and the geographic spread didn't resemble known hemorrhagic fever outbreaks. The Athenian plague spread through a single densely packed city, not across regions through direct contact with bodily fluids as Ebola does. Without surviving samples, scientists could only speculate. The real challenge was finding preserved tissue from victims, samples that still contained traces of the pathogen's genetic code, and that hunt seemed hopeless until excavations in Athens uncovered something extraordinary. Mass graves in the ancient Kerameikos cemetery, just outside Athens' city walls, yielded skeletal remains from plague victims. Inside the teeth of these skeletons lay preserved DNA. Teeth are particularly valuable for ancient DNA analysis because the dense enamel and interior pulp protect genetic material from degradation far better than other tissues. Researchers at the University of Athens extracted DNA from dental pulp and used PCR sequencing to search for bacterial and viral fragments. Their study, published in the International Journal of Infectious Diseases, marked a turning point. Instead of relying on ancient descriptions alone, they finally had microbial evidence. The graves themselves showed the human cost, bodies piled in layers, hastily buried without ritual, suggesting fear and urgency. Entire families had been consumed by the epidemic, leaving no time for proper farewell. This genetic breakthrough gave historians and scientists their first solid lead in over 2,000 years. Modern science brought sharper tools. Instead of testing for single pathogens, researchers turned to next-generation sequencing. This method takes tiny DNA fragments from ancient teeth and reconstructs them using powerful bioinformatics, comparing results against vast genetic databases. It allows hidden microbes to be identified even after thousands of years. Further genomic analysis, conducted at institutions including the Spanish National Research Council and published in proceedings from multiple journals, pushed this work forward. In secure laboratories, scientists handled bones that once belonged to plague victims, carefully avoiding contamination from modern bacteria. The results revealed something unexpected. The strongest evidence to date points to Salmonella enterica cerevar typhi, the bacterium responsible for typhoid fever, as the best fit for the Plague of Athens. Confirming typhoid fever as the likely cause required more than a single DNA match. Scientists followed a rigorous process. First, they extracted genetic fragments from multiple teeth belonging to different victims from separate burial contexts. Next, they compared these sequences against comprehensive databases of bacterial genomes, finding consistent matches to Salmonella typhi. To rule out contamination from modern sources, the same analysis was repeated in independent laboratories with identical results. Researchers then cross-referenced the ancient bacterial DNA with known modern strains, identifying key genetic markers that survived across millennia. The findings were confirmed through cross-laboratory testing at multiple institutions, including the University of Barcelona. Typhoid fever spreads through contaminated water and food, thriving in exactly the conditions that existed in wartime Athens: overcrowding, inadequate sanitation, and the breakdown of normal water systems would have created perfect conditions for a typhoid outbreak. The disease causes high fever, severe gastrointestinal symptoms, and in serious cases, intestinal bleeding and neurological complications, all symptoms Thucydides described. The mortality rate matches as well. Without modern treatment, typhoid fever kills approximately 10 to 20% of those infected. But in conditions like ancient Athens, with no understanding of the disease and no effective treatment, mortality could easily reach 25% or higher. This identification matters beyond solving a historical mystery. It demonstrates how quickly disease can devastate a population when war, overcrowding, and collapsing infrastructure converge. The lesson resonates today. Modern cities facing conflict or natural disasters remain vulnerable to similar outbreaks when water systems fail and sanitation breaks down. The discovery also shows the power of ancient DNA analysis to correct centuries of misinterpretation. For over 2,000 years, the Plague of Athens was compared to smallpox, bubonic plague, and hemorrhagic fevers, shaping false parallels in medical history. These errors encourage researchers to draw wrong lessons when modern epidemics appeared. Now, with genetic evidence pointing to typhoid, we understand the outbreak in its proper context. Not an exotic disease appearing mysteriously, but a bacterial infection spreading through contaminated water in a city whose infrastructure had collapsed under the pressure of war. In 430 BC, Athenians faced war, hunger, and a disease that seemed beyond explanation. For centuries, the cause was misnamed and misunderstood. With DNA sequencing from mass graves, Athens finally revealed its secret. The plague that killed Pericles and devastated the ancient world's greatest democracy was most likely typhoid fever, a disease we now understand and can prevent. Thanks for watching. If you enjoy how genetics is rewriting what we thought we knew about history's deadliest outbreaks, make sure to like and subscribe so you don't miss the next discovery. This is Hidden Strata,